Hi, everyone. Sorry again that I can't be here this morning, but I'll see you on Wednesday. I hope you had a wonderful Christmas break and a wonderful New Year. Today we start into chapter 7, which is rotational motion. And you might say, oh, wait a second, why spend an entire chapter on rotational motion? Aren't most things just moving in straight lines? Well, think about it for a brief moment. You're on a planet that's rotating on its axis, revolving around the sun. The sun itself is revolving. Our entire solar system is in part of a galaxy that's rotating, and we're moving around it as well. Our galaxy is caught in rotation in the supergroup. Most of the universe is actually in rotational motion. Very few things actually move in a straight line, which is why we spend a whole chapter, and actually part of next chapter, talking about rotational motion. It affects more things than you would think. So, quick review. Let me explain the problem here before we get into it. Rotating objects are very common, but describing them is rather difficult. For example, look at the rotating blue wheel. You're like, oh, this is easy. It's rotating counterclockwise, and it's moving at a certain speed. But think about it for a brief moment. Um, which direction is rotating? Well, some people would say, oh, it's going to the left if you look at the top part of it over here. And some people would say, oh, no, 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 it's going to the right if you look this part here. Some people would say, oh, no, it's going up. Some people would say it's going down. And if you check real quick, it's actually moving faster at the outside. And this is also interesting. You might say, counterclockwise is fine. But if you looked at this wheel, well, first of all, here's the velocities. It's moving faster at the outside edge than the middle, covering a greater distance in the same amount of time than the middle part. But the direction that it rotates depends on your perspective. If you were standing on the other side of this wheel, it would actually appear to be rotating clockwise. It's hard to visualize that. So the velocity is different at each point, and the direction of rotation also depends on which side of the wheel you're standing on. So we got to come up with some new ideas to describe rotating objects. So yeah, velocity is now that way. Quick review. Remember radians? Radian is just a unit of angular measurement. It's defined, you might remember from math class, as the arc length divided by the radius. And it's pretty straightforward. So if you want to figure out what this angle over here is, you would simply take the length of this arc in meters, whatever it is. You might say, okay, the arc length is 0.25 meters. Oh, that's really bad. My apologies. And then you would divide it by the radius. I know it's not reasonable. Let's say it's 0.5 meters is the radius. And you would come up with an answer that would be exactly, 0.5 radians. Now, I'm going to speak a little heresy here just for a brief moment, but I need to mention it because otherwise later in the year or later in this semester or chapter, we're going to run into problems. What do you get when you divide an arc length in meters by a radius in meters? Well, the units actually cancel out, and this number right here should actually be unitless. You're like, well, wait a second, where's this radians come from? Well, it's just a notation that mathematicians add just to express what this number is. This is heresy in the math department, but radians don't exist. They're not a true unit. This number, when you calculate theta, is a unitless number, but we put radians there just for convenience. Later in this chapter, we're going to have places where the radians seem to disappear. That's because they were never there to begin with. Don't let it panic you. All right, moving on. We can now use this idea for some very simple ideas. Just a couple reminders again real quick. 1 revolution is equal to 360 degrees, which is equal to 2 pi radians. How would you convert from degrees to radians? You could very simply just, remember, go factor label. If you had degrees and you wanted to go to radians, you could just multiply by a fraction, getting rid of this or getting rid of degrees, put 360 degrees over here, put 2 pi radians up on top, and your answer over here would tell you how many radians. Oops, I ran out of space. How to convert revolutions to radians? Same kind of thing. If you had revolutions and you wanted radians, just do a little factor label. We want to get rid of revolutions. We want radians. And you might remember that there's 2 pi radians in each one revolution. And if you multiply this out, you would get radians. So it's pretty easy to do the conversions if you needed it. Nothing too terrible there. Moving on, though, let's try something real quick. Some quick examples of angular displacement. An automobile wheel has a radius of 42 centimeters. If the car drives 10 kilometers, through what angle has the wheel rotated? And you're like, whoa, wait a second. How in the world am I supposed to calculate that? Well, think about it for a brief moment. To calculate theta in radians, all you have to do is take the arc length, which in this case is the circumference of the tire and the distance that it rolled. And if you think about it carefully, the outside edge of this tire has rolled 10 kilometers or 10,000 meters. Converting the radius into meters as well, so 42 centimeters becomes 0.42 meters, you'll discover that the wheel has gone through an angular displacement of roughly 23,800 radians. You could do, to convert that to revolutions, you can just do a little factor label there. Again, 1 revolution for each 2 pi radians, and you'll figure out that many revolutions. And if you had to do degrees, you could do the factor label this way, taking the revolutions here, 360 degrees per 1 revolution gives you that many degrees, a hideously large number. Or you could even take the original radians number and do 360 degrees over 2 pi radians and get the same answer. So converting angular displacement, pretty straightforward. We usually work in radians, but sometimes problems might have revolutions or degrees in it. The axis rotation is always the center of the wheel. And we always use a fixed reference line. You can choose any point you want, but usually we use the positive x-axis, just like in geometry class or math class. If the wheel is moving this direction, we would take the final theta minus the initial theta. How far did it rotate? If you notice this one, the final over here, I'm trying to figure out roughly what that would be, might be, let's say it looks like 30 degrees, but it's actually 330 degrees all the way around. Let's see, so, oh gosh, converting that to radians. Can I just write it this way? Let's say it's just negative pi over 6 radians here. And if we define our 0 point here, if you take the final minus the initial, you'll get delta theta in this case is negative pi over 6 radians. Which might seem a little strange. You're like, wait, it went through a negative displacement? Yeah, this is by definition. Things that are rotating clockwise have negative displacements. And you might say, whoa, wait a second. I thought clockwise is the normal direction. Well, think about it back in math class. In math class, we have 0 here, we have pi over 2 here, we have pi over here. So when you're rotating this direction, you're actually increasing your angular position. And so our angular displacement increases if you go counterclockwise. It's based back on trig. Yeah, I guess I should put over here, there's the 2 pi over 3. You get the same idea. It increases as you go around that way. All right, moving on. Here's the interesting thing about it. And you might say, well, what's so handy about this angular displacement thing? Well, if you remember the first slide, different points in the wheel are undergoing different velocities, different meters per second. But for a rigid body, and this is the critical part, it's rigid. That means they're all fixed together. One point can't move separately from the rest of it. Every point on an object that's rotating undergoes circular motion around the center. And all the objects on this rotate through the exact same angle during the same time. So example, your bicycle wheel, a DVD or Blu-ray disc, clock hands, your hard drive if you have a mechanical one. Every single object on that goes through the same angular displacement in the same time if it's a rigid body. Now, there's one little problem with that. There's some things that are not rigid. For example, the planets in our solar system do not go through the same angle in the same amount of time. Water going down a drain, it rotates faster as it gets close to the drain, so the angular displacement's greater as it gets close to that. Hurricanes or typhoons, same thing. The angular displacement's greater when you get close to the eye of the storm. So things that are not rigid don't have those same angular displacements. Just real quick, we already talked about this. every single point undergoes the same angular displacement in the same sometime t, which you can sort of guess where I'm leading into this. The new idea here is angular speed. Every single point on a rigid body has the exact same delta theta in the same amount of time, delta t. And we're going to define a new quantity here called the average, or just the angular speed. Angular speed is a lot like velocity. Remember, regular velocity was the change in position over the change in time? Angular velocity is the change in theta over the change in time. Now, just a quick note on this one. Let me write the old equation up here. Velocity is defined as the change in position or displacement over the change in time. Angular speed is represented by a Greek letter. This is omega, lowercase. Av here stands for that. By the way, just here's your Greek lesson for the day. This is lowercase omega, and this is the way it's drawn. It looks almost like a W, but officially it should have a little curlicue in here. And this is capital omega. So we're using lowercase omega to represent angular velocity, and it's the change in theta, delta theta over delta t. Same kind of thing here. If it's rotating in this direction, we say we have a positive delta theta, which means we have a positive angular speed. So far, so good? All right. Instantaneous speed would be as if you took it over a very small time unit. But the more interesting I want to mention right now are what are the units for angular speed? Since delta theta is measured in radians and delta t is measured in time, it's simply radians per second. And again, it's positive if the thing is rotating counterclockwise, and we have a negative angular speed if the object's rotating clockwise, just by definition. And some of you are saying, well, wait a second, how do we know which is counterclockwise and clockwise right now? Again, remember, it depends on your perspective. For now, we'll just simply define it as if it's in the plane of your textbook and rotating clockwise, it's a negative, and if it's going counterclockwise, positive. There's a better definition coming, but just wait for it for a moment, I promise. There's still some old-fashioned units or other units for angular speed that's out there. For example, if you look at your car's dashboard, you usually have a speedometer, and you also have an RPM meter that indicates the angular speed of the engine. And that's usually represented as RPMs, revolutions per minute. And you can also sometimes find RPSs, revolutions per second. Again, remember, each revolution is equal to 2 pi radians, so you can convert it real quick if you need to. Here's the example problem real quick. Old vinyl records, this is all way back when, played at a constant angular speed of 33 1/3 RPMs. If you had to convert that to radians per second, what would it look like? It would look something like this. So you've got 33, and I'll just go 0.3 revolutions per minute. And do a little factor label. We want to convert revolutions to radians, so I'll put revolutions down here, radians up on top. So 2 pi radians for 1 revolution. And over here, real quick, we need to get rid of minutes. So 1 minute, and we need seconds, 60 seconds down there. And if you multiply this out, you'd end up with the answer in radians per second. And I don't know what it is off the top of my head. It's driving me crazy. Omega can also be written as 2 pi over capital T, and this is a new thing here for us. Capital T doesn't just represent time, it's a very specific time. It's the period or time required for 1 revolution. You can also write omega as 2 pi f, where f is the number of revolutions or rotations per second, where f represents a frequency. So let me do some quick examples. So up on top here again, here's the definition of angular speed, angular displacement over time, or you can write it as 2 pi over the period, or 2 pi times the frequency. A commercial jet engine, when it's not at full thrust, is usually operating about 250 RPMs. This is for a large one. What's the angular speed in radians per second? You can do some quick factor label. You've got revolutions per minute, 2 radians per revolution. That gets rid of the revolutions and gives us radians. We need to get rid of the minutes. And so again, factor label, 1 minute is equal to 60 seconds. And if you convert this all or multiply it through, you'll end up with 262 radians per second. What's the fan's period? Here we can do the same kind of thing. Once we know omega is equal to 2 pi over the period. Solving that real quick, so we get that is equal to 2 pi radians over the period. The period, it only takes 0.024 seconds for the blades to go around once. It's pretty quick. And what's the fan's frequency? Same kind of thing as well. Just plugging in the numbers here, you'll discover that the frequency is 41.7, and the units are 1 over seconds, if you think about it. That's radians. Frequency has to be 1 over seconds to get radians per second. 1 over seconds is used so frequently in physics, it's actually given its own unit, the hertz, which is abbreviated capital HZ, or Z, sorry. Hertz. Whoops, not very well. You've seen hertz before, megahertz, gigahertz. It's a frequency that's used on radios, on your computers, all over the place. So you'll find those kind of units. So hertz is the unit for that. All right. Here's the direction part, and it's a right-hand rule. So take a look at that record that's spinning right there. According to what's called the right-hand rule for this one, so the difference here is I need to point out this is angular velocity. Just like regular velocity is a vector quantity, it has magnitude and direction. Angular speed just has a magnitude, but if you find the direction of it, you're defining now angular velocity. And here's how it works. If you take your right hand, and it's got to be your right hand, and curve your fingers in the direction of the rotation, so it's rotating this way, your thumb points in the direction of the angular velocity, which in this case is straight down. And you're like, what? Sorry, it's omega, which is in the negative y direction, or in this case, they labeled it z. So for this object rotating in this direction, if you use your right hand, you could try it right now, it's pretty hilarious. And you put your right hand and point your fingers in this direction, you'll find your thumb pointing down. In the negative, and they've got it negative z, I would actually call it negative y. And that's why this clockwise rotation is defined as negative. You're like, what? Yeah. So if you can also do it this way. So this kind of rotation is in the negative direction. And this is how you find the direction of omega. So omega doesn't point in any particular direction, or doesn't point along the rotation, but actually in a plane that's out of, or not in the plane of the rotating object. The beauty of this one is, if anybody looks at this rotating disk, if they put their fingers up here and do it, they'll discover their thumb is pointing downward. If they put their right hand fingers rotating this way here, they'll also agree that it's pointing downward. The beauty of the right hand rule is no matter from what perspective you look at it, you'll agree on the direction of omega, or the angular velocity. So omega is used both for angular speed and angular velocity. If it's the vector, which includes the direction, we usually put a little vector sign above it. Some really quick examples of this one. So in this case, we're going to look at angular displacement and speed. The Leaning Tower of Pisa, if you've ever been to it, is slowly moving. It's still tipping over slowly. Not very fast, 1.2 millimeters per year on average between those years. What's the angular displacement? Just plug and chug. You'll discover the angular displacement per year is pretty remote, or is really tiny. What's the angular speed? If you take delta theta over delta time, here's the number of seconds in 1 year, you'll discover that its angular velocity is crazy slow. I have to use scientific notation to even show it to you. But it's basically plug and chug. Another quick example. Oh, I don't know if I've done this one yet. The Earth rotates once on its axis every 24 hours and has a radius of that. What's the average angular velocity of a point on the Earth's equator? How would you calculate that? You would just take, so again, angular velocity is equal to delta theta over delta t. And in this case, it would just be 2 pi radians per day, that's one rotation, divided by the number of seconds in 1 day, which is 86,400. Sorry for a moment. And if you divided that out, that would give you the angular velocity of a point on the Earth's equator going around this way right here. Here's the interesting thing. What's the average speed of that? There you would have to actually figure out for this velocity the change in x over the change in time. And that would be the circumference 2 pi r divided by the period. And by the way, you'll notice that's almost exactly the same as here. If you simply took omega times r, the radius of the Earth, you'd figure out this. Sorry, I don't have a calculator handy to solve it, but it's pretty quick and plug. Here's the interesting point. What about at the North Pole? If you're at the North Pole, you still rotate once per day. So your angular velocity is the same as it was before up here. It's still 2 pi over 86,400 seconds. Sorry, I got to put my radians in there as well. But your average speed, this gets kind of fun. What's your displacement per unit time? Here's the big difference. Whereas the equator, you're booking along here if you solve this. What's your velocity here? Believe it or not, it's 0 because you rotate at one axis. You might say, all right, my hands have some velocity. But talking about the actual North Pole, or the point at the North Pole, it actually doesn't move. Another one here, what's the angular velocity in radius per second? Again, just a quick plug and chug one. You just have to convert this 100 or 12,000 RPMs, revolutions per minute, and just do some quick factor label, get rid of the revolutions, and get rid of the minutes. 1 minute is equal to 60 seconds, and you could solve it. If you might have realized already here, if you're calculating velocity, or let me quick write this, omega is 2 pi over the period, and velocity is 2 pi r, the circumference, divided by the period. Notice the only difference between these two. So if you simply take omega and multiply by the radius, you'll get velocity. And so this last one here, you've got to design helicopter blades so that the tip of them don't go beyond Mach 1, or the speed of sound, which is about 340 meters per second. So you could actually calculate this real quick. If you know omega up here, if you want to make sure that it stays below that, you could calculate what omega would have to be. So actually in this case, you're going to calculate the radius. So you would take the omega you solve up here in radians per second, take it down here, and then solve for the radius. Pretty straightforward. I'll solve these as well with you later. Brain break, I'll skip for the moment. Oh, you saw it. The last topic I want to talk about real quick is angular acceleration. Angular acceleration is represented by the Greek letter alpha. And as you might have already figured out, regular acceleration is defined as the change in velocity over the change in time. Angular acceleration is defined as the change in the angular velocity over the change in time. This is the Greek letter alpha. This is lowercase alpha, looks like a fish. This is capital alpha. You're like, wait, it looks just like the Roman A. You're right, it is. But this is Greek lesson 201. It's defined as the change in omega over change in time, and it's pretty straightforward. The units for it, as you might have guessed, since this is in radians per second, and you're dividing it by seconds again, you'll end up with radians over seconds squared, or radians per second per second. So here again are the units. Positive accelerations are in the clockwise direction, and negative accelerations in the counterclockwise direction. For a rigid object, again, every single point has the same angular velocity, and therefore, since it would have the same change in angular velocity, every point on a rigid body shares the same angular acceleration as well. Instantaneous would technically be as you let time shrink to 0. Don't let that stress you too much. But you're looking at the angular acceleration at a single point. Usually you look at the graph and find the slope of, let me quick draw it so you can make more sense. If you had a graph of omega versus time, and you wanted to figure out what the angular acceleration was at this point, you could just find the slope of this graph. why the slope is change in or rise over run, which is by definition that. So you could find the instantaneous acceleration here by drawing a tangent line to the graph at that point and finding the slope of that. All right. Last two slides, I promise. We're almost done. Just like linear acceleration requires a net force, angular acceleration requires the rotational equivalent of a force, which is called a torque. And torque is represented by the Greek letter tau. Tau looks like this. Some people are like, wait, how do I draw that? I sometimes describe it as a pie standing on one leg. So here's a pie. Here's tau. Curve. And you can just draw a straight line down instead of that. This one's got a little fancy doop-de-doo on the bottom, but you don't have to do it. The definition of torque is officially this. And I don't know if you've seen this yet in math class or if you've ever seen it. Officially, torque, tau, is equal to the radius vector cross product the force vector. And cross product is a way of multiplying two vectors. And I'll talk about this more next chapter, but for now I'll just show it to you. And if you happen to run into cross products before in math, some of you are like, wait, that means it's outside? Yeah, don't just save it for everybody else for a moment. The angular acceleration then, once you know the torque, is in the same direction as the torque. Just like, if you remember Newton's second law, F net equals ma. In that one, the acceleration's in the same direction as the net force. The rotational equivalent of Newton's second law looks like this. And I know some of you are like, whoa, wait a second. So in this case, instead of force, we have net torque. Instead of mass, we have this new variable. It looks like capital I. It's called the rotational inertia, which we'll talk more about next chapter. And instead of linear acceleration, A, we have alpha, the angular acceleration. So here's the definition of torque. Once you know the torque, you can use this equation to find the angular acceleration. Or if you know the angular acceleration, you can figure out what the net torque is. So these two equations are our new ones for this chapter. We'll spend more time with these two next chapter, but I wanted to show them to you. And you might say, oh my goodness, I've got a whole nother set of equations to memorize? Well, yes, but also no. I'm going to give you a quick hint into what I'm going to show you on Wednesday. You'll notice there's some nice correlations. I haven't given you this equation yet, but take a look at this. Final omega is equal to initial omega plus alpha times t. You're like, whoa, where'd that come from? Or delta theta is equal to initial angular velocity times time plus 1/2 angular acceleration times time squared. And this one, final angular velocity squared equals initial angular velocity squared plus 2 times angular acceleration times delta theta. Holy smokes. Some of you are like, oh yeah, we see it, Mr. Clomber. Yeah, it's easy. The answer is these are just like the formulas you already know. All you have to do is translate the linear components into their angular equivalents. Velocity becomes angular velocity, omega. Acceleration becomes angular acceleration, alpha. Displacement, x, becomes angular displacement, theta. Time stays the same on both sides. But you can translate every single equation you've ever learned into the rotational equivalent without actually memorizing all these new equations. I'm going to introduce the idea of, I'm going to call it the physics Rosetta Stone. It's on the back of your assignment sheet. I'll show it to you in a moment. But the Rosetta Stone, if you don't already know about it, is a stone that was actually found in a fort in Egypt, which had ancient Egyptian hieroglyphs, Demotic and Greek, parallel translations all next to each other. And up to that point, no one knew how to translate hieroglyphics, but everybody knew Greek and Demotic. And so after this stone was found, it gave us a primer to be able to translate all the hieroglyphics. On Wednesday, I'm going to give you that same primer. Although you already know a few of them, I'll give you the rest of those pieces. Good luck with worksheets 1 and 2. You can work together, and I'll see you on Wednesday.